here because we organized a collaboration between his university, Sejong University and Seoul and UPC. So it will give an opportunity to students to travel there for doing some research or part of PhD, etc. Well, he's a doctor for the Northwestern University in United States, and he's in Sejong University, now a professor and the dean of his faculty. He will give a talk on electronic device applications in two-dimensional materials. Thank you.
Thank you very much for introduction. I must appreciate Professor Nuria Ferrer to invite me to this nice place. And this is my first time to visit Barcelona, actually. It's quite impressive, very nice place. Okay, let me start my lecture or talk. And the title, as already mentioned, Electronic Device Applications in Van der Waals Two-Dimensional Materials. Yes, many people know about two-dimensional material nowadays because the graphene was the really astonishing materials since they found it. And so many applications are already suggested and demonstrated. And here's, I'm concentrating on another two-dimensional material rather than graphene, which is actually so-called traditional dicalconized materials. Anyhow, I will let me introduce the Sejong University. Probably students will know, I hope, where is Seoul, but it's in the far east side of Asia. Yes, I marked as a circle, and Korea, North Korea, and South Korea, and Seoul is in actually this place, the capital of South Korea. And Sejong University is located in the eastern part of Seoul, inside Seoul. Yeah, this is the campus. This is actually Seoul. This is just campus view. Let's go into the my talk, actually. The outline of a presentation will be two-dimensional material introduction. After that, I will introduce three kinds of electronic devices which I've studied so far. And finally, I make a summarize for that. There are three kinds of two-dimensional materials based on the band structures. And here I categorize like this. And first one is the material without band gaps, and also shows a linear, the energy and momentum relations, dispersions. And probably you have heard about the graphene. Graphene belongs to this category, no band gap, and also if you see the structure of a band structure, it shows a straight line like this. We call it actually Dirac fermions, which follows slightly different category, which is a massless particles. Second category will be bilayer graphene, which has an inverted band structure like this. Because this material is really special, although they just made of two layers of graphenes, since they have an inverted band structure, there will be the basis for so-called quantum spin-Hall effect. Such things are very active nowadays. And third case is phosphorine, or which I also mentioned about traditional matter dicalconized, and also graphene. Graphene is a graphene which is attached by the hydrogen atoms like this. In such category, material shows band gap. So it might be regular things as you seen in the semiconductors, but however, this band gap becomes important compared to the graphene. The reason is application. I'll tell the application shortly, but let me introduce the transition metal dichalconate first. And the structure of this material consists of M and Q something 2, like this. M corresponds to the transition metal, will be molybdenum and tungsten and so on. Such metals can be M. And Q side can be chalcosium, the sulfide or selenium or tellurium, such that ones. This material shows, like a graphene, you can create the materials to make the really two-dimensional ones. So the fabrication of material for the device is very similar as a graphene. However, this material has band gaps. That's a different thing. That's also important things. Nowadays, the CVD growth on oxide silicon wafer for this transition metal dichalconate material is very active. There are some examples here. Although this silicon is not belongs to this kind of material, silicon actually corresponds to the same category as the graphene ones. They don't have band gaps and such things. But however, they're also very interesting material which can be grown on some to large area two-dimensional material. They are also very effective and active area of research. As I mentioned, the band gap of two-dimensional materials are important. The reason is for use logic devices or something like switching devices, you need band gaps. Disadvantage of graphene is they do not have band gaps. So if the graphene in itself cannot use it as the element for the logic circuits, they have to intentionally make some band gaps on graphenes if you want to use for the logic devices. However, TMDC, as I told you, this kind of material can have band gaps like this. It is well above 0.4 electron volts, which means it can be used as switching element. So this kind of material becomes very popular nowadays for the applications. And interesting thing is, as a bulk, this material shows indirect band gap. However, if they make the single layers, they become a direct band gap. And also the size of band gap a little bit increases. This is a well-known properties of that. These two material does not belong to this material, TMDC material, but however, I put it here because this is also important material as a substrate, because this material does not give us dangling bond like a silicon substrate. So these materials are very important for other two-dimensional materials as a base. Although we can introduce a good band gaps in two-dimensional transition metal dichalconate, but however, the problem is there are some calculations. As band gap increases, the mobility actually decreases. So actually, it's kind of compensations. If you want to have a very fast react material like graphenes, you don't have band gap. But for the switching material or logic material, you need band gaps. So as band gap increases, the problem is actually the mobility goes down. So you have to have some compromise, which means if you choose something like MOT2 or WS2, whatever, and might be, it could have a relatively large mobility, and also those materials could have some, band gaps for logic devices. This table shows the mobility of two-dimensional materials. And I put down some world record mobilities. For single-layer graphene, 2.5 million centimeters square per Bohr second. Such very high and very good material. But however, as I told you, this material cannot use as a switching material or logic materials. So if you switch to the MOS2, this one, single layer case, the mobility goes down like this. So it's a quite, low mobility. But however, this mobility is, compared to the normal matter, is quite high. So it's still very useful material. So such a way, you can choose some of your TMDC materials for your applications. Another important thing for the material as a semiconductor is doping, because you want some P-type or N-type to make, for example, PN junction or diodes, such things, and transistors. And doping is very important. And by the way to have doping, I listed here, there are so many kinds. One is, for example, the gas adsorption. The other may be chemical solutions. You can use it to make some P-type or N-type dopings. And for me, my experience said, N-type two-dimensional material is quite often you experience. However, P-type, you will find a little difficult to find it. And which means, which has a high mobility and P-type two-dimensional material is actually challenging. Although the study or this one shows they claim they have a good material, but however, if they read more carefully, the mobility of this demonstration is quite low. Anyhow, the P-type or N-type of two-dimensional material is important for your applications. So far, is some introduction. Let me go into the real experimental sections here. First of all, I'm going to concentrate on PN junctions out of two-dimensional materials. 2014, there are first report of PN junctions made of two-dimensional materials. The BP stands for the black phosphorus. So it's made of many layers of phosphorines. And the bottom layer is molybdenum sulfide, disulfide. And the P-type material becomes actually the black phosphorus, become a P-type. And MOS2, the bottom layer, is actually N-type material. So kind of just putting together, stacking together, without doing anything, they make PN junctions. The interaction between those is actually van der Waals force. So it's a very interesting and astonishing junctions. They're putting together, they make PN junctions. The property here shows very nice electrifications. The RR ratio probably, I could tell about 10 to the 4 or something like this. And after this, demonstrations, there are a couple of demonstrations as well. And similar materials, but this junction also can be active in the infrared range. So they can use it as a photo detectors as well. So because the two-dimensional material is quite transparent, so also you can put it on the flexible substrate. This device is a very interesting material. You could make something like a flexible photo detectors out of these materials. Here's another report, and actually a report done by our group. And so another category is like this. Not just simply two-dimensional material. The P-type silicon substrate is a regular substrate. By putting on just N-type two-dimensional material on that, without doing anything, they could also make PN junctions. So one is the P side is substrate itself, and N-type is those two-dimensional material just by putting there. And they can make electrification PN diode behavior like this. So this material is quite interesting, right? Without growth of a semiconductor, we could have semiconductor PN junctions easily. Here's another thing, shows, the black phosphorus and WS2, other kinds of two-dimensional material, they could have also PN junctions. There are so many examples. And the property of this material also shows conventional PN junctions, like they shows Jenner diode breakdown, also avalanche breakdown, when they apply the quite high reverse bias. And probably people know Jenner diode breakdown to originate from the high electric field in the depletion layers. And this avalanche breakdown comes from scattering of the electrons. They knock out of the valence electrons, and then they make avalanche of currents, which is called as avalanche breakdown. Anyhow, what I'm showing this PN junction shows conventional behavior for the regular PN junctions out of semiconductors. However, the layer itself is just the van der Waals, direct van der Waals force junctions. And quite recently, however, there are some, questions about those kind of reports, because so far they show nice rectifications. In this letter, nano-letter paper, they claimed the demonstrations so far is not from real PN junction. They claim is the electrification is out of context. Contact means they always have some metal context in those materials. Metal contact to two-dimensional material. So they make the Schottky barriers. That is why you have rectifications so far. So this paper says the reported, the evidence for the rectification is not from the heterostructures rather than actually contact effect. They claim that. So I'd like to focus on that one. Is it really, is there just PN junctions out of two-dimensional materials, or like they say, all reports are just not correct. All reports are just the Schottky barriers. So what is true? So I'm going to say you the answer here in next pages. Schottky barriers, this is for understanding for the students. And if one side is metal, the other side is semiconductor, if you put it together, the bend structure of semiconductor will bend it like this, bending. And the quantum barrier is called the Schottky barriers. Because of that, and if you apply a bias current like this barrier height becomes high, so eventually current cannot flow easily. But however, if you bias like this, which is called the forward bias, the current can flow. So which shows electrifications simply by metal and semiconductors. So like this, we have metals and semiconductors. The other side, another metal. If you see that one, you might think, okay, there are two Schottky barriers. But however, Schottky barrier is not always happen. It depends on two kinds of contact. One is ohmic contact, the other is Schottky barrier contact. Depends on the work functions of metal and the electron affinity of the semiconductors. If the difference between those are high, you can expect the Schottky barriers. However, if the work function of matter and the electron affinity of two-dimensional semiconductors are similar, we would expect the ohmic contacts, which means they doesn't show Schottky barrier contacts. And if you measure directly by using IV curves. You can prove which side shows Schottky barriers. Actually, if you use that chrome gold context, you could have a nonlinear IV curve, which shows there is a quantum barriers, which correspond to Schottky barriers. However, the aluminum contact side, actually they made ohmic context like this. Why I'm making this one is I like to prove really the observed rectification is coming from Schottky barrier itself. So one side Schottky barrier, the other side is ohmics. So I can use this device as a test device to do the experiment. I saw actually the rectifications without any p-n junctions between 2D materials. It shows rectifications. So I can conclude all the report might be they are just reporting the behavior of Schottky barriers as a rectification effect. But what about, then my question is, what if I make really p-n junctions out of 2D materials by making the metal context as an ohmic context, both sides? Do I really expect no p-n junction behaviors or not? And here's a technique I can make those kind of material. Because I know how I make ohmic contact of Schottky barriers, I can make the ohmic context for both sides like this. For example, my group chose MOT2 is a test materials, which is a molybdenum telluride. So tellurium, telluride, okay, sorry. So MOT2 I call it. So I can make this material as a P-type or N-type by doping. My doping technique is just to shine a deep UV light like this. If you shine deep UV light, this material originally was actually P-type material after irradiated by the deep UV. By deep UV with flowing nitrogen gas, I can convert this material as N-type. I will show the proof of this one in the next experiment. But anyhow, I can also choose the special metal which correspond to, when P-type, the Fermi level of this one, the MOT2 is lie on the valence side. So we could choose some material, the work function correspond to actually the valence electron and the energy of the P-type MOT2. So palladium is actually right material for that. For the N-type MOT2, aluminum will make ohmic contacts like this. Whatever it is, the proof can be done by IV curve for both metal and semiconductors. Here shows the evidence for the ohmic contacts. And the palladium contact to P-type MOT2, it shows straight lines. It's most like ohmic. And the other aluminum contact to N-type MOT2 shows a straight line, which shows actually the ohmic contacts. If I switch the materials, the IV curve becomes all nonlinear. So I can prove, okay, my strategy is okay. So I can make ohmic contact to the two-dimensional materials. So next thing is P-type MOT2 characteristics by applying a backgate. Okay, so this is a current conductance. So it's a negative backgate. It shows conductance. So which means this is a P-type. Positive backgate. And you have a flowing current, which means actually N-type semiconductor. So this MOT2, after shine by the deep UV with the nitrogen gas, it becomes like this. So I can make a single MOT2, I can make P-type as well as N-type. Anyhow, by using those two, the two-dimensional materials, I could make contacts like this. So after that, I can do experiment. Okay, I can flow current from aluminum side to palladium in such way. So, which means although all contacts are ohmics, I really looking at the van der Waals junctions between p-type MOT2 and n-type MOT2. So which shows actually very nice actually electrifications. So I prove actually, this might be the very recent one actually a month ago. So I did not publish yet, but I will, proudly show the student of Barcelona. Yes, in UPC, I'm happy to show this one. It is actually, the evidence of PN junctions purely by the two-dimensional materials. So people might ask, what is the advantage of PN junctions out of two-dimensional materials? Actually, if you have a very nice, PN junction behavior by conventional semiconductors, why those are important and interesting? One important thing is very low temperatures. Such things, conventional, the PN junction does not work. Actually. But this kind of material, the origin of a PN junction is not depletion layer, this kind of material. Actually. People said this is a depletion layer free PN junctions, and which means actually by the band bending, simple band bending, that will show Schottky barriers, and because of that, and even very low temperatures, and PN junction works actually, like a helium liquid helium temperature. That's why another important applications probably, if you have some ultimate environments, then you need some real electronics, like electronics should work in the space or something. Might be two-dimensional material is the answer. And keep going. Listen, our work is actually the way to make PN junction is not simply bilateral device. You could stack like this and directly, purely vertical way you can make PN junctions as well. And here it also shows nice rectifications here. But anyhow, there are so many interesting things you could make it by using two-dimensional materials. So this is one part actually. I'm going to have a three-part. Actually, one part is finished now, and second part is called spin-dependent tunnelings, and I'm going to talk about this one. Story is like the spin-dependent tunneling, and the study maybe begins from the Zorozhansky 1975 about between two ferromagnets. If there are tunneling between those, they call the tunneling magnetic resistance may exist. Theoretical study was actually suggested at that time. After that, kind of experiment and also the model they suggested by Juliet, which is by measuring tunneling magnetic resistance, one can estimate the polarization of magnetization of each ferromagnet, which is suggested by Juliet. And it is 1976. And also the first demonstration of room temperature spin-dependent tunneling is by Budera in 1995. And the concept is very simple, actually. To make magnetic tunnel junctions, you could stack just ferromagnetic, metal, and some thin insulator, for example, aluminum oxide, and another ferromagnetic material, like a nickel ion and cobalt ion. Such things can be ferromagnetic materials. Such a you could make magnetic tunnel junctions. It is actually element of your the memory disk. Yeah. So it's a TMR. When the magnetization of both ferromagnet is parallel, by flowing current like this way, they have a low resistance. And if the magnetization of the two ferromagnet material is anti-parallel, So it will show high resistance. So you could have 0, 1 state like this. So you could use it as an element of memory. Here shows a real experiment, and by looking at this one, by applying a magnetic field this way, and the bottom side cobalt actually, they have a low switching field, which means they can flip the magnetization of a ferromagnet by using lower the magnetic field. So if you sweep magnetic field this way, the cobalt flip first. Then at that situation, they make anti-parallel state. If you further go down, all the magnetization will become parallel. And the magnetic field will sweep down again, then cobalt will flip again first. It shows like an anti-parallel state. And then if you magnetic field further down, all the magnetization of the ferromagnets will align that way. Such way, they could have a parallel state. Anyhow, in the experiment, by sweeping the magnetic field this way and that way, and then you could have some high resistive state and low resistive state, like you could have such a thing. By this, experiment, they claim, okay, first demonstration of a tunneling magnetic resistance. So Julia, as I mentioned, by measuring such experiment, he suggested I could tell how much spins are aligned inside of these materials by simple guessing like this. Let's say the spin polarization, if we define like that, like here, yes, here, if you see these ones, spin up, down, spin up and down populations represented by n up, n down like this. The difference of population you could write like such way. This is defined as a polarization, spin polarization in one ferromagnetic material. So TMR actually determined by conductance difference like this way. Parallel state conductance, anti-parallel state and the anti-parallel difference between those divided by parallel state conductance, actually that gives us TMR values in experiment. And if you put in G and P here, by putting the definition of the conductance, and you can put this one to this, and at the end you could have these formulas easily. Which means if you measure TMR, you could estimate what P's are going to be, which means you can tell how much spins are aligned inside of these materials. Anyhow, they can call of spin polarizations. And yeah, this is so far introductions. Let me introduce a real story here by using the two-dimensional materials. What kind of TMR we expect here? So far, conventional TMR. From now on, I'm talking about by using two-dimensional materials. So one side of ferromagnetic material is nickel ion, the other side is cobalt. The reason why I'm using two different kind of ferromagnet is because the nickel ion has a lower switching field than cobalt, which by sweeping the magnetic field, I can make either parallel or anti-parallel. But intermediate state, intermediate layer, I replace by some two-dimensional materials. For example, graphene here. So I can put aluminum oxide here like this. So first of all, when I put the graphene only without aluminum oxide, the tunneling magnetic resistance shows like this one. You see some conventional behavior like this. If I put aluminum oxide between those two ferromagnetic material, it will show also conventional behavior. But now I'm going to the third one. They combine together. It shows negative now. going down actually. What happens here? Why suddenly TMR becomes reversed? I mean, polarity of TMR reversed. Why? What is the problem here? And since to study that one at the beginning, we need to talk about like this. Oh, might be some dirty layers exists between ferromagnet. They might cause those things. So, first of all, as an experimentalist, you should have very clean, the device. You should have it, which means you have to cut down the fabrication process, which can cause any contaminations. Normally, if you make a very small samples by using lithography, and you're going to use photoresist or PMMA, such things, they cause lots of dirt on your samples. To remove that ones, I invent like this kind of structures, which means I make holes on the silicon substrate, and then I deposit one side ferromagnet like this, the other side I put something like the graphene, and after that I can put some ferromagnetic materials. Such a way, without any lithography techniques, we can directly evaporate and put a 2D-dimensional material and put another ferromagnet. Such a way, very clean interface we could achieve. Actually, we could achieve very clean interface like this kind of structures. So all these are for study why the spin polarity prepping was occurred in my TMR experiment. But anyhow, after making samples like this, or these samples you can understand simply, one side is nickel-ion, the other side is cobalt. In between, although this is a little bit complicated, you could just think simply single layer graphene is between those. You can think like that. And such one, so cobalt single layer nickel-ion junctions, cobalt standing from top to bottom, and this kind of junctions, and the result of TMR is positive like this. And this TMR actually, as temperature is lowered, the TMR becomes a little bit increased like this. This is expected because the lower temperature, the phonon vibration decreases, so you expect a higher TMR. That is not the special. However, most important thing is positive polarity of TMR here. Right? If you put single layer of graphene between two ferromagnetic materials. So these contacts shows actually as temperature is lowered, the resistance of contact decreases, which shows actually metallic behavior. Remember those two things, and I replaced the other material. Instead of graphene, I put a single layer of MOS2, and this material also shows positive TMR, and also as the temperature lower, the tunneling, the resistance of a TMR just decreased, which is actually metallic. Now I replaced actually the intermediate material like graphene and MOS2 like this. Now look at this, and the polarity of TMR actually switched. It shows a negative actually, like this. This material still shows metallic behavior. Show the next. It will show actually as temperature. I'm sorry. Yes, here, the TMR. As temperature is lowered, the TMR value itself actually decrease like this. Oh, actually, the absolute value of TMR increases, which is because the phonon temperature was decreased. So that That's expected. I'm not going to say that one. I'm going to say, okay, I did not brought these ones, but however, this material also shows actually metallic behavior. As temperature is lower, total resistance of junction actually decreases as temperature is lower. Although I don't have here the view graph. And anyhow, I'm going to say this material shows actually metallic behavior. Now I've switched the other intermediate layers like aluminum oxide and single layer of MOSE2, and those material shows actually negative polarity of MR, like shows here. And as this one, as temperature is lower, this material actually shows the resistance of a junction increases, which shows actually insulating behavior. And an more complicated one, I just make a summary like this. There are two ferromagnets here, nickel-ion and cobalt. And in between, I put some intermediate, two-dimensional materials. And first line shows a single layer graphene. It shows positive polarity, and it shows metallic behavior. For example, if I put the MOSE2 in between, it becomes positive polarity and metallic behavior. If I put something like mixed graphene and MOS2, it becomes negative polarity. Although these junctions shows still metallic behavior. If I mixed with aluminum oxide and MOSE2, and these observed TMR shows actually negative. By the temperature dependence of junction resistance shows actually insulating. In this case, aluminum oxide and multilayer graphene shows negative. So my conclusion is like this. Junction itself, however it's metallic or insulating, it is not important. If I just mix the two layers, it shows negative polarities. So it's a strange, findings, but the origin of physics is not quite clear. But however, I can explain like this. If majority spin tunneling is blocked some way, and the MR can be negative. There is a known idea, because if you think, in this case, parallel state, which means like this one, it shows a nice, the tunneling is easy, because this side is spin up, this side is spin up. Also, the electron can tunnel easily through the other side of the metal, like this. But however, in somehow, intermediate state block the majority spin tunneling. What happens is they cannot tunnel directly from here to there. They can only tunnel through this from here to there. But however, this is a spin, the magnetization this way, this is that way. To make alignment, this material has to align that way. This material has to be aligned this way. Then, tunneling from here to majority spin of one side of material to minority spins state of other side is actually enhanced, is appear. In such a way, you could explain why this negative TMR appears. Anyhow, the condition is majority spin tunneling has to be blocked when you combine two materials. Is it possible or not? There are so many reports, they observe negative TMR so far, like listed here. But however, this does not belong to our explanation, because these are just some organic material and other story. And might be possible way is the graphene might be there are theoretical report in graphene case, and it's already known the transport was dominant in the K side. But however, if you study the transport of a nickel ion, K point has actually the majority population, spin population is actually, which shows there is absent actually. So by such stories, one can tell, and spin filtering can happen if you have graphene as an intermediate state. But however, what I observe is not simply graphene. You need something else. Two combination of actually 2D materials. It shows negative, which means majority spins are blocked. So anyhow, confusion of theory, confusion of experiment so far. It is unresolved, games so far. So second talk so far was actually I suggest something unresolved thing can happen in this 2D dimensional material, but still very interesting, such topics. The last topic is inverse spin-Hall effect device. I'm going to tell shortly about this ones. And third introduction is Hall effect, actually. And Hall effect already known. And ordinary Hall effect, as we know, in the magnetic field, if electron transport like this, by Lorentz force, the electron deviate like this. So you could have a transverse voltage can be measured. But what about if we have a ferromagnetic material which have some magnetization of that one? Without magnetic field, the material itself has a magnetization. Such materials, if you flow current, depends on the spins, they deviate like that way. So spin up is deviate that way, spin down is deviate that way. But however, this magnetic field is, there is no magnetic. This magnetization is aligned that way, which causes actually charges accumulate more than the other side like that. So which cause transverse voltage like this. So this is called anomalous Hall effect. What is the spin Hall effect? Is this thing. Without any external magnetic field, if there is a spin orbit interactions in normal matters, these are ferromagnetic matters, but normal matters with strong spin orbit interactions, and the spin dependent scattering can be happened like that. So spin up can deviate like this, spin down can deviate like that. And finally, what could have is spin accumulation can happen depending on the orientation of spins. So although the number of electrons are same from this one and this side, so you don't have any transverse voltage. But however, you have a transverse spin accumulations. This is called the spin Hall effect. Anomalous Hall effect and anomalous Nernst effect is, introduced here is simple things. And instead of electric current, if you have a thermal gradient across the samples, this thermal gradient actually makes diffusive transport of electrons that cause also the transverse magnetic field, the transverse electric voltage like this, which is called anomalous Nernst effect. And those can be happens in ferromagnetic materials when the material has a thermal gradient. This is just introductions. And the next page shows a quantum Hall effect and the quantum spin Hall effect. In two-dimensional case, shows here. Quantum Hall effect is happens when you apply very high magnetic field, and you will see the Hall effect become quantized like this ones. So there occurs edge state, which is called like this. But without the magnetic field, in some material which have a very strong spin-orbit interactions, this kind of thing happens, like the quantum spin-Hall effect, which can be happen in the surface of a topological insulator, and this is called actually the quantum spin-Hall effect. Difference of this and this is this can happen in the very high magnetic field, but this can happen without magnetic field, only very strong spin-orbit interactions. Some, state is needed actually. So for this, you have only one kind of edge state, the quantum spin-Hall effect, but quantum spin-Hall effect, quantum spin-Hall systems, you have a two edge state like this. This two edge state is called the Kramer's pair edge states. What I'm going to show now is a spin-Hall effect and inverse spin-Hall effect. Those are same physical origin, but inverse means nothing, but if you flow here, if you flow spin unpolarized current, normal current if you flow it, then depends on the spin orientations. The electrons can, accumulate and spin up, spin down, accumulate in this side, and spin up, electrons accumulate that way. So spin accumulation can happen in spin-Hall effect. Now here's, if you flow already spin-oriented electrons, then only the one side, the electrons accumulate. Finally, what happens is actually you have a transverse voltage across the sample. So inverse spin-Hall effect is simply can be done by if you inject some spin polarized current into the channels, then you could have some transverse voltage without external magnetic field. Here shows some example of spin-Hall effect and intrinsic and extrinsic. This is nothing but intrinsic is from the band structure, and extrinsic comes from impurities. So the people's more interested in actually intrinsic effect, but however, so far the reports are listed here, and also the corresponding theories are listed here. And let me show something observation of extrinsic spin-Hall effect at the beginning by using the gallium arsenide. It's an N-type gallium arsenide, and which has strong spin-orbit interactions. If you depends on the condition is unstrained gallium arsenide. So here's idea is simple. If you flow a current from here to there, spin up electrons deviate, and then they accumulate this side. Spin down, accumulate that side. The only thing is how you detect these ones. In this group, they use the light, which is called as a Kerr rotation measurement. If you shine a light here, depends on the spin orientations. The effective light could have circularly polarized. If you spin up, then say right hand circle, the polarization of light will be reflected. So for the spin downside, if you shine the light here and the reflective light is left hand circularly polarized light will reflect it from this side. Such a way they can detect whether this side is a spin up or this side is spin down. Anyhow, by using the Kerr rotation measurement, they can measure locally whether spins are oriented up or down. And this middle side is the spins is not aligned. Actually, spins are, just lie in the surface. How they prove this measurement? By applying a magnetic field this way, spins can precess. So the signal should be disappear. They also did the experiment like that. They prove actually by applying a magnetic field this way, the orientation of spins are really actually precise, and they do not observe this, accumulations. So they proved the first extrinsic spin Hall effect in n-type gallium arsenide. Next experiment done by other groups shows actually intrinsic spin Hall effect is their idea is like this. Instead of they also flow current instead of the right shining by using curve measurement. They use a LED, simply like this, by flowing a current to these small channels here. Although very small here, the picture is small. If current flow from this side to this way, and at the edge there are two p-type gallium arsenide here, and also another p-type is here. So when the electrons flows and spin up accumulate this way, this side, and spin down is accumulate this way. Spin up electrons actually combine with the holes in this side, and they makes the light comes out. But that light should be circularly polarized. So by checking the polarity of a light, they found they denote as LED 1 and LED 2, and one side of LED 1 shows actually this one, and the other side shows that one, which means depends on the edge. The light came out from this LED, the spin polarization is actually different. In such a way, they can prove actually spin Hall effect exists in n-type semiconductors. More easy example by the matter can be shown by this group actually. Let's say if ferromagnetic material is here, aluminum is here. If your spins are injected from this matter to this aluminum, and if spins are aligned to the perpendicular to the surface, and you can imagine the spins are deviate by the spin orbit interactions, they accumulate one side of the aluminum channels, which cause eventually transfer voltage between those two. So actually spins are injected from this ferromagnetic one, and they measure transverse voltage between these two terminals. So such a way they can observe some inverse spin Hall effect in aluminum. These are the result of their experiment. And the last, the demonstration by old time, they also show simple things. The way of spin injection here is simply by applying the polarized light. And then polarized light produce spin-oriented electron or holes. These electrons, when diffuse out, because of spin-orbit interactions, they can accumulate one side. And they measure that one, they claim, okay, they measure inverse spin Hall effect. But so far, there are so many experiments like this, and in the matter, in the bismuth, and so on. And zinc oxide, they also measure something. Similar thing here is spins are injected from the ferromagnet, and then zinc oxide, when spins are injected from this ferromagnet to zinc oxide layer, when spins are oriented this way, they deviate one side and they accumulate one side. They measure voltage, transfer voltage between those two, which also prove, okay, there is an inverse spin Hall effect. Many, many examples. But here, what I'm going to say is, okay, there are another examples I'm going to skip. So there are so many examples and so many ways to spin injections such a way. And here, important thing here is, what about 2D materials? If you have a 2D material, for example, I chose the tungsten disulfide, WS2, one of the representative material of two-dimensional material, TMDS materials. So spins are injected this way. As I told you, when spins are aligned one side, because of spin-orbit interactions of WS2, without any external magnetic field, the magnetic field here, B, is not for to make a Hall effect. This magnetic field is only applied and to make zero. The only way, the purpose of this one is to make orientation of magnetization of the covert. So real experiment can be done by applying a magnetic field and make B zero. Just align the orientation of magnetization of cobalt, and then they injected the current, and without any magnetic field, spins are accumulate bottom side like this, and we can measure top and bottom voltage difference. In such a way, we could demonstrate there is inverse spin-Hall effect in the two-dimensional materials. So these are just the sample structures for our device. So here's the result, actually. I will explain this one. WS2 actually is an anti-material. So by applying a gate, the conductance can be happens when you apply positive backgate. So negative backgate, there's no current flows, which means it's an anti. Okay, say, first of all, you have to apply some bias voltage, either 40 volt or 60 volt, to make the WS2 as a conducting first. Electron can transfer. Now, if you remember the structure of the samples, now from the cobalt ferromagnetic electrode, spin-oriented electrons are injected. And then, for example, when magnetic field is zero, spin orientations are aligned for one side, you have transverse voltage is observed, like this way. And the magnetization orientation is reversed, and the transfer voltage are actually change the sign. So that means when you have spins are aligned that way, and you accumulate electrons, the bottom size of your channels, if you flip the magnetizations, spins are accumulate in the upper side. So such a way you could measure the voltage drop across the samples. And such experiment has done here, which means it's proof of existence of inverse spin-Hall effect in two-dimensional materials. And more proof of that one is, okay, if you align your magnetization in this way, what happened, instead of injected spins are oriented not this way, if you orient it like that way, the channel is that way, spin is injected that way, there is no, deviation of electrons. Actually, spins for the inverse spin-Hall has to be, if you inject it that way, you could deviate like this. If spins are aligned upward, and electrons can deviate like that. If your spins are oriented like that, that is actually deviate like that way. The upper part. So anyhow, depends on spin orientations. Detecting of inverse spin-Hall effect terminal should be chosen correctly. So here since the spins are aligned that way, your detection should be top and bottom. If spins are aligned, if you align the spins that way, there is no deviations of electron by the inverse spin-Hall effect. So such test experiment, you can prove your measurement is really from the inverse spin-Hall effect. This is the proof of that one. Another thing is, interesting is like that. Let's imagine spins are aligned this way. And so when current flows from spins are aligned this way, in plane orientations, and then injected that in plane spin orientations can accumulate the bottom side of these channels. They can measure voltage. Now the same situation, if the current flows that way, what happens? In plane orientation is that way, but diffusion way, the transport of electron is that way. It actually accumulates upper side. So which means you can observe a flipping of transverse voltage. Why either you can flow that way or that way, you should see the reverse of polarity of your transverse voltage. This is the proof of actually inverse spin-Hall effect. Yeah, another evidence of whether they might question whether they're really can he inject the spins into the two-dimensional materials, and we can confirm by so-called non-local measurement, which means actually this is very standard measurement for this field. Actually, spins are injected for one side. The spins are injected from here to there. They're measure voltage other side. In such way, they could observe something spin accumulations, which is called a non-local measurement. Anyhow, this is a kind of proof of spin injections. If I summarize everything here, depends on the inverse spin-Hall voltage, and depending on the distance from the injector to the detectors, we can vary the distance and the strength of a spin-Hall. The transfer voltage you can draw, and it is observed like this. This observation can be fit by the formula, which is exponentially decay by the distance from injector to the detector. And by fitting that one, what you can have is how strong is your inverse spin-Hall effect. The most important parameter here is actually, which is called the spin-Hall conductivity. This is compared to other material, this is quite strong, which is almost correspond to the tungsten actually. The tungsten, because of they have a very heavy atomic numbers, so they expect very high spin-Hall conductivities. Here's WS2 also, because we already expect, because this consists of W, which means tungsten, we expect a high spin-Hall conductivity. So the conclusion is two-dimensional materials. These materials are also, serve as a good candidate for the spin-Hall conductivity materials. Here are also the study whether so far I talk about the inverse spin-Hall effect actually. Oh, sorry. Inverse spin-Hall effect here. There are questions about what about the so-called inverse Lashiva-Edelstein effect. What's the difference of this spin-Hall effect and the Lashiva-Edelstein effect is, you can simply think like this. In true two-dimensional case, there is a real two-dimensional materials. If you have large spin-orbit interaction couplings are there, then you could expect the Lashiva-Edelstein effect. What is a Lashiva-Edelstein effect is simple. It is if you have some current flows in two-dimensional systems, you expect, because of a Lashiva effect, you could expect spin accumulations. The equation you could like this. Okay, let me explain simply. Okay. If you have, this system is actually the AG and bismuth, they expect actually two-dimensional system was occurred between those interfaces. And spins are injected from the nickel ion by using the FMR. Anyhow, let's say these spins are effectively injected like that way. And at this surface, since spins are injected to this surface, and that injected spins actually can cause voltage drop across samples. So which is actually stated this equation. That is actually Rashba-Edelstein effect. So condition is like this. One condition is you should have a two-dimensional system. Second thing is you should inject some spin polarized current into that two-dimensional systems. That at the end, what you observe is voltage across the sample. That is Rashba-Edelstein effect. Might be very similar as the inverse spin-Hall effect. Remember inverse spin-Hall effect, I told the similar thing. Spins are injected, and because spins are oriented because of strong spin-orbit interactions, they accumulate one side. We measure the voltage, transverse voltage across the samples. Here's condition is the only thing is a two-dimensional case. Spins are injected, and those injected spins cause the voltage drop across the sample. Actually, statement is very similar. The only difference is extreme two-dimensional limit, approximation is actually the Rashba-Edelstein effect. If you have something like depth or thickness of those things, you could say inverse spin-Hall effect. People might misunderstand those things. Actually, inverse spin-Hall effect and the Rashba-Edelstein effect is quite different things. But however, I can conclude that is only the terminology. Okay? So anyhow, another thing is to observe Rashba-Edelstein effect, actually the spin orientation is a little bit different because in this way, spins has to be aligned that way to make transverse voltage drop like that way. Many experiments have been done to observe the Rashba-Edelstein effect. But however, what I'm claiming here is the observed effect in my WS2 system, which is not Rashba-Edelstein effect. That's what I'm going to say, actually. The reason is my WS2 has some thickness, actually. So it is not really a two-dimensional system. And we cannot expect the so-called Rashba, the spin-orbit coupling in our systems now. The reason simply is to observe that one. Rashba-Edelstein effect, to observe that one. Magnetization has to be aligned that way, and if you inject the current, and you could have a voltage drop across these things, like this way. And if you measure some voltage drop from those tools, you could claim you observe Rashba-Edelstein effect. But in real experiment, I do not see such effect at all. So simply say, in my case, WS2 does not make any ideal two-dimensional electron gas here. It's just, just a thin materials. So it's not simply, we cannot make a Rashba-like system in our system. So the observed effect, we should call it as just the inverse spin-Hall effect. So long lecture, I'm going to conclude now. The summary is like this. First part of my talk is more like a little bit interesting. I'll say the Van der Waals PN diode with a real ohmic contact has realized. I'm going to take that one. And second thing you might brought with you is two-dimensional material magnet tunnel junction. There are some issues in TMR polarities which has to be studied more. But however, experimental evidence are clear here. The third part of my talk is inverse spin-Hall effect in tungsten disulfide crystals. actually the fourth sentence is most important thing is there are still much more room for two-dimensional materials for students should study actually this active field. Okay, thank you very much for attending these lectures. Yeah. Okay.
Actually, one device is there's only one device between one layer and another.
Yeah.
Inside the layer is not.
Oh yeah, inside is not. But people said like this: two-dimensional materials, like graphene, so layer by layer. Between layers, okay, this side, the in-plane interaction is very strong, sp2 or whatever. But across the layers, people said that is van der Waals. So, but what about if you put together different one layer here, the other layer just put together, that is definitely van der Waals, without nothing else. If you make a real chemical bond, actually you have to do something else, not sitting on here like this. People has to do something treatment, high temperature annealing or something things they should have to make a real chemical bond. So for my case, it's just sitting on. That's it. Yeah. Yeah. Frankly speaking, I don't know either nowadays. But I know there are a lot of issues to make real two-dimensional superconductors. I couldn't remember the exact material. Yeah. 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 Yes. Yeah. But so far it's like this, and those fields is not really go with TMDC materials now. The calculinized, as I told, nowadays are more oriented to the applications. Yeah, and they are more interesting to make PN room temperature and PN junctions, and also even they make as a transistor actually. I do not show here. My group also works at transistor actually, and in such a way. There is definitely interesting things and the superconductors. We have to answer whether there is a real two-dimensional superconductor. We should actually. There are, yeah. I agree. Yes, in physics, as a physicist, we should study that as well. Definitely. I'm on T2, yes. Yeah. Yeah, yes. Yes. Mm-hmm. Oh, actually, our experiment is done in the normal just environment. So we don't need actually vacuum and we don't need anything. To make, only thing is here, as I told you, only thing here is actually, okay. Anyhow, the reason is actually when you measurement, next page. We stop. Anyhow, to make at the beginning, if you buy from the company, there's MOT to mostly P-type. Okay. And then the reason why P-type is like this, because impurity already there. Yeah. But you have to remove the impurity to make N-type. So how do you effectively remove that things? Mostly what I believe is some oxygen-based things. To remove that one, you have to flow actually N here to combine with the oxygen and make the NO2 or NO3 like that. And also you need the energy. So you have to apply some energy by using deep UV. So effectively treatment of surface. So it becomes N-type. So that's it makes such way. Yeah, yes, inert.
But we can use argon or
Well, whatever, argon may not, because you need something combined with the oxygen, actually. So the reason is choosing the nitrogen is I would like to make NO2 or NO3 or such things. Yeah. Yes, those are whatever way to remove the oxygen. That is the way. Yeah, some energy and removing oxygen is the answer.
Thank you very much.
Thank you very much.